Hello students, welcome to Stanovich Chapter 10. We're actually going to also do Stanovich Chapter 11 lecture in just a minute. I think these two go really well together and they're both fairly short as well. I believe an earlier version of the book might have had these chapters as one chapter and then it expanded on 11, so separated them. Anyway, they go really well together. Let's start with Stanovich Chapter 10 on probabilities. So our discussion today of probabilities builds really well on our discussion of interactions. So variable 1, 2, and 3 make variable 4 more likely. Variable 1, 2 make variable 4 more likely, but if variable 3 is in there, it makes variable 4 less likely. These kinds of things are what we're talking about with probabilities. So probabilistic trends essentially mean that something is more likely to occur. So if something is highly probable, it means that it's pretty likely that will happen, but not that it's necessarily going to happen in every single case. So if there's a 90% chance of something happening with variable 1, 2, and 3 in play, well, if you see variable 1, 2, and 3 in play, most of the time that'll probably happen, but not every single time. So that's what probability means. It means something is more or less likely to hold true or to be related or to happen. So there will always be a person or an argument that there's the person who doesn't fit this trend. So even if the trend is pretty strong, it almost always happens. That time that it doesn't happen does not necessarily cancel out the effect or the predictive value of this probabilistic relationship. So we know that people who smoke cigarettes, it's a lot greater likelihood of developing lung cancer. Just because you have an uncle who smoked every day of their life, 2 packs a day, and didn't get lung cancer, that doesn't mean that this trend doesn't hold. That for most people that smoke, that person still has a higher likelihood of getting lung cancer, even if they don't actually get lung cancer, right? So there's always going to be, especially when we're dealing with probabilities, specific situations, anecdotes, examples where it doesn't quite fit. And yes, we want to do a better job as scientists to fit all of the data, but probabilities are one way that every science works to get to better and better predictions. So many of us know a person who might smoke a lot for 40 years but never develops lung cancer. That doesn't mean that this trend, that smoking cigarettes increases your probability of developing lung cancer. So that is still true, even if we do know a person who didn't fit that trend. So most sciences work a lot in probability, and we'll get to p-values and probability values essentially, and the chance of things. And different sciences have different standards of how much surety or how much probability is acceptable. But let's talk about that. So our understanding of psychology, physics, biology, geology, dinosaurs even, are based really heavily on probability. So when we're using probability, when we're making predictions of it's most likely that this will happen, or it's most likely that this happened, or it's most likely that these go together, we often use what's called inferential statistics. And we've mentioned these before. Essentially, we measure a sample and then we infer, we're using inferential statistics, we infer something about a population. So, a population, let's redefine these again. We've talked about them before earlier on in class, but a population is everybody in the group. So the entire population. The population of the world is 7, 8 billion, something like that, right? So that's the entire population of the world. You could also talk about the entire population of the United States. You could talk about the entire population of the state of California. You could talk about the entire population of Salt Lake Community College, right? You could talk about specific populations. It's everybody in that group. So an example is the ethnicity of all the people in the USA. What is the ethnic breakdown of the entire U.S. population? Well, we can get a sense of that because we do a census in the USA. We try to measure every single person. Now, we're not going to absolutely get everyone, but we get a pretty good number of everybody. So, a sample, on the other hand, is your study group, the group that you select out of that population and then study. So, if I wanted to know about the population of the USA, I would get a sample. Maybe I would sample 200 people from each state. right? So that would be a pretty good sample of the US population, right? It's not everybody, obviously. So, but 200 people from each state is a pretty good group to then be able to infer something about everybody in the USA. So, let's say I got the ethnicity of 500 people from across the USA. So I did a random sampling. Maybe people saw a social media post or something and clicked on to put their ethnicity in a little survey. So I get a pretty big sample across the USA of 500 people. So my sample is that 500 people. Maybe there's more people from California or more people from Hawaii or more people from New York in my sample, but that's my sample, right? And then I'm going to infer something about the population. So this is a graph from census data and data from 2019 about the USA, about the ethnic breakdown. So we see a couple of the bigger groups of ethnicities here in the US. So this is just displayed in a graph, and I want to compare it to so that's the population, right? So we're looking at the US. We could do this for the world. The graph would obviously look a lot different if we looked at the population of the world, right? But this is the population, the entire population of the US and the ethnic breakdown. So this is another way to graph that. So this was data from 2010 with the different ethnicities. This is a bar graph. So this here was a pie chart. This is a bar graph. So it's just demonstrating them in different ways. This is also trying to infer population in 40 years, so estimate what things will look like. But really what we're looking at is basically this graph here and this graph here are saying the same things. Obviously the numbers are slightly different because this one's 2019, this one was 2010, but this is another way to look at this. This is called a histogram. You will often see histograms like this in psychological statistic reports, so in your results sections of your papers. Oftentimes histograms are a pretty useful type of bar graph to demonstrate a lot of data. So here we can see 2016 data for ethnicities. And then here they're also trying to project out to 2060 what ethnicity breakdown there will be. All right, so again, the lighter blue here lines up with this graph and lines up with this graph. Obviously, this one's 2019, this one's 2010, this one's 2016. But it's three different ways to display the same data about an entire population. So pie chart, bar chart, histogram. This is another example of a population graph. This is actually a graph of the population of heights broken down by men and women in the USA. So you can see there's a normal distribution of heights. So in inches, the average for men is closer to 70. The average for women is closer to 65, 66. So you can see the graph there. You could put these two together and see another general for population without any kind of sex or gender breakdown for what it is. But here they've separated those. So you see two different normal distributions. So again, this is a frequency distribution, another way to graph this. So one thing that we can look at is the difference between these distributions. Hopefully you can see that these little arches here have a bunch of data. So there's a few people over here, lots of people under here. So that's why the arch is bigger in the middle here versus the arch is bigger in the middle here. And there are some people this tall and this tall. So this is kind of simplifying it. It just shows the two graphs based on just their normal distribution. Right, so still looking at the population, we're showing this breakdown, and it's not clear whether they were looking at sex or gender here, but that's the breakdown that they're trying to look at. And so we see an average. So the average for both is right here at the top middle of that normal distribution. You can get a sense of how spread out these are. The blue one is a little bit more spread out than the red or pink one here. But this is another way to graph a population's data set. Now, those are all populations from the US. Now, what about a sample? How might your sample be different, or how might your sample be the same? When we're inferring something about a population, we are hoping that our sample is very similar to the population. And that's what we want. We want our sample to be similar to the population. But depending on the sample we gather, it might not actually be very similar. So this on the left is population breakdown of the USA for ethnicity, and this is ethnicity in Salt Lake City, Utah. So not all of Utah, just specifically Salt Lake City. And you can see, obviously the colors are different because a different designer designed these two. But you can see the biggest group here and here are both white, and they're about the same percentage. But you can see, based on the colors, it looks like this one is Hispanic, so it looks a little bit bigger than this group. The black group in the US versus Salt Lake City are much different though, right? So if you wanted to take your sample from only Salt Lake City and you had this ethnic breakdown here in Salt Lake City versus this is the breakdown of the US, and your variable was in some way related or ethnicity was in some way important to your variable, would just sampling from Salt Lake City be a good idea if you're trying to generalize to the whole population of the US? So generalize means, let's say I find that finding, I find some correlation, I find some relationship, I find some experiment that shows that certain ethnicities do better or worse on certain things or are more or less correlated with certain variables. So I find that in Salt Lake. Could I say that that might be the same for those same ethnicities in the population of the US? So inferential statistics, that's what we are trying to do, but depending on our sample, we might not be able to do that. So I couldn't actually find a height breakdown graph for people in the US, but this leads us to a good question. Would it be different? So this is the population graph for height differences in the USA. Would it be different in Salt Lake City or just Utah? So let's say a sample in Salt Lake City. Let's say we sampled people in Salt Lake City. Would the graph of heights be different? Why or why not? So pause really quick, maybe take a couple notes, make a note of why you think it is or why you think it's not different, and then I will continue for a second. So I don't actually suspect it would be different. I suspect if we got a big enough sample from people in Salt Lake City, I don't really see any reason that people in Salt Lake City would be shorter or taller on average than the population of the United States. So we might find a slight difference, like we might even find something statistically significant, which will hopefully make sense if you've taken a stats class, or in a few minutes when we cover statistical significance. We might even find a statistically significant difference, but is it an actual real difference? Probably not. We might find slightly higher, like slightly taller for one or both of these groups, or slightly shorter for one or both of these groups. But I really don't suspect that the height difference from people in Salt Lake is much different on average than the USA. So if your variable was related to height, well, if there is no difference between your sample and population, you might be able to infer something about that population based on your sample. So most sciences work in probability. Psychology, physics, biology, chemistry, geology, all of the science do work on probabilities. They use inferential statistics. So they look at a sample. They look at a sample of rocks. They look at a sample of creatures. They look at a sample of organisms. They look at a sample of data from particle colliders colliding particles together, right? That's not every single particle in the universe that they're colliding to test, right? They're testing a sample, and they're doing it enough times to get enough data to say, we're pretty sure that this is what's going to happen. So that's essentially what an inferential statistic is. We take our sample, we do, let's say, a survey or an experiment, and we hopefully have enough people in the sample that we can say something about the population at large. So take data from sample, you bring your sample in, you have them do your study, you have them do your experiment, your survey, you get your correlations, you get your results, and based on your results from your sample, you infer, you make generalizations about the population. So if your sample is from 500 people across the USA, then you would make inferences about the people of the USA as a whole. Now, let's say you have a correlation between well-being and education level in your sample. People with higher education levels also tend to have higher well-being. So there's a positive correlation there. You might be able to infer that the population is the same. But what could be some things that would lead your sample to be in such a... What might cause you not to be able to infer things about the population? So write down a couple notes. So let's say we took a sample of 500. We found this correlation. Is there any reason we wouldn't be able to infer something about the population? So write some notes. Answer this to yourself. So one of the big things is if your sample is too small or too different than the population, you might not actually be able to infer things, right? So let's say we took a random sample and somehow all of our random sample was older, like much older than the general population. Maybe all of our sample was different ethnicity on average than the general population. All of our sample had clinical depression. Versus the general population isn't everybody, right? So if your sample is too different, you probably can't infer something about the population. If your sample is too small, so let's say rather than getting 500 people, we only got 50 people. That's not enough variety of people to say something about the US as a whole. Even 500 people, that might not be enough. Right? Maybe if you replicate that finding again, that could be good. But 500 people, even at that point, I'm like, I'm not so sure. Because let's say you did an experiment. That's 250 people in a control group, 250 people in an experimental group. That's not a ton of people compared to how many people are in the USA. So if your sample is too small for the claims that you make, that could be a problem. So most sciences do work in probabilities, and an example of this is that 16%, I read that too quickly, 10.6% of adults in the world are left-handed. So 10.6% of the world population is left-handed. So the probability of you running into a left-handed person is that about 1 in 10 people that you meet are left-handed. So if you meet 10 people, it's a pretty high probability that one of them will be left-handed. If you meet 20 people, almost certainly you will have met one person that's left-handed. Similarly, 8% of adults in the USA own a motorcycle. So, similarly, your probability of meeting someone who owns a motorcycle, you'll probably meet at least one person in every 10 to 11 people you meet that own a motorcycle. So 8% of white males have color blindness. So about 1 in 10 or 1 in 12 or 1 in 11 people, white males that you meet, will have color blindness. So just imagine that, like going about your day, you meet 10 people in your day, probably one of those 10 people were left-handed, right? So that's how probabilities work. This is how we use probabilities for predictions based on our samples for our studies. So one interesting finding I recently found in some of my dissertation research was that about 13% of my samples had done something heroic. So I definitely need to test this in more samples. I need to replicate this in more studies. But it looks like if you meet about 10 people, it's high likelihood that at least one of them has done something heroic, which is a lot more than I ever expected. So I'm really excited about this finding. I really want to investigate it further. But that suggests the probability of meeting a hero might be a lot higher than I ever thought before, based on previous research. And this is why we use this kind of research and why we look for probabilities, so that we can know more about humans, about all sorts of things in science. With this being said, as scientists, we do need to be careful about how we use and understand probabilities. We need to be sure that we're interpreting them accurately and using them accurately as well. So probabilistic statements about behavioral trends, like most people tend to behave this way in this kind of situations, can be dismissed by people. And that single person who doesn't follow the trend might let people discount it. Say, oh, well, I had an uncle who didn't get lung cancer. They smoked so much. They didn't, so that's not a real finding. Well, that probabilistic statement is true, that it's your much higher likelihood to develop lung cancer from smoking cigarettes. Just because one person doesn't discount the rest of that data, right? So this goes back to something that Stanovich started the book with, that some people don't understand the science and will discount psychology because they might, in this instant, actually know someone who doesn't fit the trend. When you're talking about, say, particle accelerators in physics, a general person doesn't interact with a particle accelerator. They don't have a sense of when the evidence might not align with that, or a specific example where it didn't quite fit, but they might know a specific person who doesn't fit this psychological concept you're talking about. So it might lead them to, with cognitive dissonance, just throw away the thing that they just learned. It tends to happen, and it's one reason we need to be careful about how we use and understand probabilities. We want to make sure that we are being accurate in what we're saying. So about a little over 10% of people are left-handed, so you're pretty likely in meeting 10 people to meet one person who's left-handed. So those of you who are watching this who are left-handed, it's like, I've met someone who's left-handed right now. The fact that any given finding or treatment doesn't apply in every case for some people might make them less likely to trust psychology. But that really is the case for all sciences. There are instances where it might not always happen exactly that way. Like maybe the temperature is slightly off, or the molecules are not exactly in the right order or something for some kind of reaction to take place, right? So those individual instances where they know a person who doesn't fit that trend can lead people to say, well, psychology isn't scientific. I know this, maybe even 2 examples that don't fit that. Doesn't mean the probability is not the case. So there are examples in physics, in biology, in all other sciences where examples that don't always follow the probabilistic trend. We want to get the best as we can at having the highest likelihood, knowing all the interactions to be able to make the best predictions, but those are still generally based on inferential statistics and probabilities. So there will definitely be cases where it doesn't always follow the trend. It doesn't always apply. This medicine works for 99% of people. Yeah, for 1% of people, then that medicine's not going to work, right? So we need to be clear about what these things mean. And we need to understand that for a lot of people, when they hear about these results that don't fit in psychology, it does lead them to more often discount psychology as a whole. So any individual case might not be able to be predicted down to the letter accurately, but probabilities do allow us to predict pretty well and pretty accurately, especially when we look at group trends. So if we knew that everyone who is left-handed did better, or like 95% of people who are left-handed did better in math classes, then we could pretty well predict, hey, you're left-handed, there's a pretty good likelihood that you will do better in a math class. I just made that fact up. I don't actually know if that's true. But if that was the case, well, there would be some left-handed people that didn't fit that, right? That would be getting below average scores. So the prediction of outcomes based on group characteristics is called aggregate or actuarial prediction. And that's what this chapter and the next chapter really talk about, is actuarial prediction. So getting an aggregate amount of data, an aggregate amount of results, building those patterns of results like we've talked about to make an actuarial prediction. So let's talk about this in the context of when using these kind of actuarial predictions might go wrong or might go bad. I want to make you bigger. There you go.
Welcome to the TEDx Sonoma County stage, Todd Rose.
It's 1952, and the Air Force has a problem. They've got good pilots flying better planes, but they're getting worse results, and they don't know why. And for a while, they blamed the pilots. They even blamed the technology. And they eventually got around to blaming the flight instructors. But it turned out that the problem was actually with the cockpit. Let me explain. Imagine you're a fighter pilot. You're operating a machine that in some cases can travel faster than the speed of sound, and where issues between success and failure, sometimes life and death, can be measured in split seconds. If you're a fighter pilot, you know that your performance depends fundamentally on the fit between you and your cockpit. Because after all, what good is the best technology in the world if you can't reach the critical instruments when you need them the most? But this presents a challenge for the Air Force, because obviously, pilots are not the same size. So the issue is, how do you design one cockpit that can fit the most individuals? For a long time, it was assumed that you could do this by designing for the average pilot. That almost seems intuitively right. If you design something that fit for the average size person, wouldn't it fit most people? It seems right, but it's actually wrong. And 60 years ago, an Air Force researcher, Gilbert Daniels, proved to the world just how wrong this really is and what it was costing us. Here's how he did it. He studied over 4,000 pilots, and he measured them on 10 dimensions of size. And he asked a very simple question. How many of these pilots are average on all 10 dimensions? The assumption was that most of them would be. Do you know how many really were? 0. Gilbert Daniels proved there was no such thing as an average pilot. Instead, what he found was that every single pilot had what we call a jagged size profile, right? Means no one's at the same on every dimension. And this makes sense. Just because you're the tallest person doesn't mean you're the heaviest. It doesn't mean you have the broadest shoulders or the longest torso. But this is tricky because if every pilot has a jagged size profile and you design a cockpit on average, you've literally designed it for nobody.
All right, so I'll pause it there. We'll come back to this and what the Air Force did to solve this problem. But you might be able to guess. Do I need to go a little further back or a little further forward? Oh, here we go. So here is the jagged profile. So in psychology, we could imagine this in the sense of a bunch of different variables, right? We look for the average on a lot of things. What is the average of our sample? What is the average of the population? And we try to make predictions based on that, right? So this goes back to our chapter on interactions. If you know all these different, how many was it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 variables. If you know all those variables, putting them into your interaction equation, doing regression equations, you can get a better prediction for this individual who has this height, this weight, this reach, this torso, this shoulders, this chest, so on and so forth, right? You can get more individualized predictions for individual people. You can make better predictions overall, but what this also shows us is just using the average on any 1 or 2 variables might not be the best way to go. It might lead to us designing something for the average person when the average person doesn't actually exist. Right? So being able to have a better sense of all the different variables will help us make a better prediction, make a better actuarial prediction. So let's see what the Air Force ended up doing with this data.
A problem. And their response was bold. They banned the average.
So the Air Force banned the average in the new planes they were buying.
Meaning that moving forward, they refused to buy fighter jets where the cockpit was designed for an average-sized pilot. And instead, they demanded that the companies who built these planes design them to the edges of dimensions of size. Meaning that rather than design for, say, the average height, they wanted a cockpit that could accommodate as close to the shortest pilot and the tallest pilot as the technology would allow. Now, the companies that made these planes, as you could imagine, weren't happy, right? They argued and lobbied, and they said it's going to be impossible, or at least impossibly expensive, to build a flexible cockpit. But once they realized that the Air Force wasn't going to budge, suddenly it was possible, and it turned out it wasn't that expensive. And in fact, they made great strides, leveraging simple solutions that we all take for granted in our everyday lives, like adjustable seats. And as a result, the Air Force not only improved the performance of the pilots that they already had, but they dramatically expanded their talent pool. And today, we have the most diverse pool of fighter pilots ever, but here's the thing. Many of our top pilots would have never fit in a cockpit designed on average. So, most of us have never sat in a cockpit.
All right, so that's what the military did. They made it so that there could be more variability in the specific planes. And we can do that in psychology with understanding how the variables interact to make better predictions, to make interventions that work better for certain people or certain groups or certain things, right? So that is part of what we use these samples to get at, to figure out these probabilities, figure out how variables interact so we can make better predictions. So next we'll talk about how to decide how much difference is enough difference to say it's meaningful. All right, so how do we decide how much group difference is enough difference? We talked about this a little bit when we were talking about experiments. You have one group get a higher score in the quiet room versus the loud room, but how much of a difference in score is enough to say this is actually different between these two groups? That's what hypothesis testing is all about. So probability is what we use in this testing. We generally, the biggest possible probability that we allow is called an alpha of 0.05 or a 5%. So probability that basically what this probability means is that there is a 5% chance that this result came from chance. Okay, that's what this 0.05 means, that's what the 5% means. So let's say our groups are different. This is our score in the loud room. This is our score on the test for the quiet room. How big is that difference? And then we test these things and we test what is the probability that this result is due to chance. If there is a 10% chance that this result came from chance, we say, well, that's way too high. We can't be sure that that's actually a true difference between these two groups. Versus something like this, we might see, oh yeah, this is a much lower chance. There's only a 0.5% chance. So 0.5%, like put a point before this 5. So this one might be a 0.5% chance that this result came from chance. That we can be really pretty sure that this is a true difference. So another thing that we can look at, and that more of psychology is moving towards, is looking at the effect size. So we look for the probability, then we look for the effect. Is this a big effect? Is this a lot of points difference? Is it very little points difference? That's what the effect size is about. So this is only a couple points versus this might be a lot of points. All right, so with this, we want to look first for the probability. If it looks like it's a relevant probability, that there's a low percent chance that the result came from chance, then we look at the effect size. All right, so what we're doing with this is called null hypothesis testing. The null hypothesis, also called H0, and written this way, so H0 being like not being none or nothing at all, so H0 is the null hypothesis, and that's the hypothesis that there is no true difference, that the IV did not have an effect on the DV, that our quiet versus loud room didn't have any effect, that the populations are actually equal in real life, that any difference we see just came from chance. That's what the null hypothesis is, that there is actually no difference. So the research hypothesis, labeled this way, is that the IV did have an effect on the DV, that our quiet versus loud room did make a change, that the population means are not actually equal, that these observations are caused by some non-random cause, probably the thing we're studying. So, and any observed difference might actually be a true difference. That's what the research hypothesis is. So basically we look to reject the null hypothesis. We look to reject that there is no relationship, that there is no effect. So we're trying to falsify the null hypothesis. And here's a couple graphs. So here again, this is normal distributions. This is a few points lower than this one. You see this is the treatment did better at the study end. So how much difference is enough? How can we have enough of a difference to say there is a big chance or there is a low enough chance that this result came just from chance? So IV again had no effect on DV is the null hypothesis. Research hypothesis would be that this treatment actually had an effect, actually was the cause of this. if there's a 50% chance that this difference came from chance, that's not enough, right? Then that's a really high likelihood. That's like flip of a coin likelihood that this difference is just chance. So as we talk about null hypothesis testing, we either reject the null hypothesis or we fail to reject the null hypothesis. You might hear that said as accepting the null hypothesis, but the actual terminology is failing to reject the null hypothesis. So if we reject, let's say there is a 0.001% chance that this difference came from chance. That's a very low probability that that came from chance. So we can reject the null hypothesis. We can say we are pretty sure that this difference actually came from chance. So if we fail to reject the null hypothesis, let's say there's a 50% chance that this difference came from chance. Well, here we fail to reject the null hypothesis. We cannot be sure that this difference is not just coming from chance. All right, so would you reject the null hypothesis here? Would you reject the null hypothesis, again being that this result came from chance? Oh, I left some draft text in here. Oops. Well, in this case, you can't say, right? You don't have enough information. There's not enough data on the screen for you to decide if the treatment actually works. There's literally no numbers here. So here, in this case, the baseline score, the pretest score, was 4. For the control group was 4.1, and for the treatment group was 4.2 was the score. Let's say this was a test where you could get 5 total points or something, or a creativity score, and your treatment was trying to increase creativity. Let's use the creativity example. So everybody started at a creativity of 4. The treatment group is now at a 4.2, and the control group is at a 4.1. And n equals 30. That is how many people were in your sample. So 15 people in this group, 15 people in that group. So did the treatment work? Probably not. You can not reject the null. I would fail to reject the null in this specific case because that difference is probably very likely just from chance, right? The control group is 0.1 away from the baseline, and this one is only 0.1 away from the control group. The p-value is probably very high. There might even be like a 70% chance that this came from chance. Too few people. We'd need a bigger sample if this was an actual true difference. So what about here? I changed the numbers around. The pretest score on creativity was 3 for both groups. Then after, the control group was at a 3.5 on creativity. The treatment group, though, is now at 5.5. Here we still have 30 people. Would you reject the null hypothesis? Did this treatment actually work? I'd actually need to see the p-value, right? This is still not enough information for me to conclusively decide that I would reject the null. I would have to see the actual p-value. Here, though, I can make a much clearer claim. So the baseline here for creativity was 4. At the study end, 4.05, so very little change in the control group. 4.2 for the treatment group. And this was 250 million people. So half of that was in the control, half of that was in treatment. I can be pretty sure with 250 million people, this isn't a really big effect size, but I can be pretty sure that I would reject the null hypothesis. This is a true difference here. So what is the probability that this result came from chance? Actually running the statistics on this, the p-value is 0.001. There's a 1% chance that this result came from chance. So is that low enough for you to conclude that this treatment works? Well, it works. It doesn't have a very big effect. It works only a little bit and only increase creativity a little bit. But depending on what you're studying, that effect size, that little change, might be really important. All right? Let's say something like seeking help when you are suffering from depression. It's a very difficult thing to do. So making someone even just a little more likely to seek help can have a really big impact on their life satisfaction and their well-being of life overall, right? So even a little change like that, depending on what you're looking at, can be really dramatically important. So knowing that your treatment does even just a little bit make a change is important. So p equals 0.001. That means there's a 1% chance this result came from chance. I would absolutely reject the null hypothesis. This looks like it's probably a true difference. All right, So, when you're thinking about this, what probability of being caused by chance is acceptable to you? A 1% chance this result came from chance, or is that too big? A 5% chance this result came from chance, or is that too big? A 10% chance this result came from chance? What about 25% chance this result came from chance? So think on your own. What is the maximum that you would accept? So on your own sense, if there is a 5% chance that the result came from chance, is that too high or is that okay? What about a 10% chance? What about 25% chance? So the researchers who study hypothesis testing and scientists in general have basically accepted a specific standard. They've accepted a 5% chance for most psychology studies. Most of my research, I use the 1% chance actually here, but the baseline for most journals in psychology says 5% is the biggest probability that it could be related to chance. I usually use the 1% chance though, myself. So 10% chance, way too high. Nobody actually uses that in any science that I'm aware of, because that is just too high of a percent chance that the result came from chance. It's like a 1 in 10 chance. That's way too high. So let's watch this little video about probability and get you a sense of what this actually means. Before watching this video, grab a coin. So grab a coin, any kind of coin. It can be penny, quarter, whatever it is. Grab it and flip it 10 times and just record how many heads and tails you get in a row. So like first row is heads, second throw is heads, third row is heads, fourth throw is tails. Like just mark that out. So right now, before watching the video, pause this video and go and get a coin, flip it 10 times.
Good morning, John.
All right, hopefully you've got your coin. Hopefully you did actually pause it, because that's what they'll actually request you do at the beginning of this video.
I need you to do me a favor. Go and get a coin and flip it 10 times. Actually, everyone who's watching this video right now, pause it, go get a coin and flip it 10 times. Now, every flip of every coin is going to be entirely random. But despite that fact, I know what just happened when all of you flipped your coins. I don't know what happened to your coin, but I know what happened overall. And that is because I'm a psychic. Because I am omniscient. Because I have a little camera installed in all of your rooms, and I watch you as you watch me. Okay, not actually. It's because I know about probability. In fact, as this video will probably get viewed tens of thousands of times, I can guarantee you that right now there are a bunch of people who are like, holy crap, man! I just flipped a coin 10 times and it landed on heads every single time. I have a magical coin, I should take it to Vegas and bet on it because it always lands on heads. But guess what, my friend? There's nothing special about your coin, and there's nothing special about you. I'm sorry. You're a beautiful snowflake. You're very special. Even if the odds of getting 10 heads in a row are over 1 in 1,000, which they are, they're 1 in 1,024. Assuming that there are 102,400 people who just flipped their coin 10 times, there are roughly 100 people who just flipped 10 heads in a row, and 100 people who just flipped 10 tails in a row. This is probability. It is the science, the act, nay, the art of assigning meaningful numbers to things that no one can actually really know. Probability lets us make real, predictable, and measurable conclusions about random events.
So with that, hopefully you did flip your coin. If you got 10 heads, or actually if you got higher than 8 or higher, send me an email, let me know that you got that many. In every time I've done this in a class, the highest I've gotten are 7s and 8s. So I've had maybe 2 people get 8s before. Generally I get maybe like 1 person every year who gets a 7. Or like each semester that I do this, I generally get like 1 or 2 that get a 7. But I've only gotten maybe 2 people who have gotten 8 in a row, whether it be 8 heads or 8 tails. So if you got 8 or 9 or 10, definitely let me know. I just want a sense of like, I've now asked X number of students do this. At what point am I going to have someone who does get the 10 in a row? I think it'll be a really exciting day when it happens.
The thing about random events is that when they happen once, you have no idea what's going to happen. But oftentimes, when they happen many times, patterns are obvious and unavoidable. So let's do a little terminology now. Probability is just P. The event that we're looking for the probability of is expressed by a letter, usually starting with A. So the probability of A happening is P of A. And if all outcomes are equally likely, P of A equals the number of events in which A is true divided by the total number of events. So when you all flipped your coins, each individual flip was entirely random. No one, not Miss Cleo, not Albert Einstein, not even Dr. Manhattan could know where that coin was going to fall. But there are two possible outcomes, and getting heads is one of those outcomes. So there is a 1 in 2, or 1/2, or 0.5, or 50% chance that it will land on heads. So
hopefully that makes a little more sense now that we've been talking about this and you've seen these kinds of results. So a 5% chance that the result came from chance, a 50% chance. Hopefully this video helps you understand that a little better. We'll watch just a few more minutes. The extra math, don't be scared of it. I'm not going to ask you to calculate probability, but if you understand math and are grasping this, then this might help a lot, actually. So we'll watch about a minute more of this. So a 0.05 would be a 5% chance that a result came from chance.
And on heads. So when we flip 100 coins, roughly 50 of them are going to be heads, and 50 of them are going to be tails. And we expect some variation around those numbers. Okay, duh, obviously. But what if we're curious what will happen when we flip 2 coins? Then we're talking about the probability of A and B happening. Very simply, we have a 1 in 2 chance twice. And that is 1/2 times 1/2, and assuming you know how to multiply fractions, that is 1/4. A 1 in 4 chance that you will get heads and then heads. But then, if we're doing it 10 times, we have 1/2 times itself 10 times, which we can write as 1/2 to the 10th power, which my calculator tells me is 1 over 1024. This is how I could pretend to be so smart before. Now let's take things much more complicated and talk about dice instead of coins. It's not actually any more complicated. So if you're rolling a die, the total number of outcomes is 6, and maybe we're concerned with whether or not you're going to get a 5. That's one possible outcome. That's 1 over 6.
So this might be useful if, rather than just having a 50% chance, maybe you know more variables. You know there's a higher chance, or you're trying to predict one outcome of many outcomes. That could be like what we're looking at with these dice. Holy crap! How crazy that you have a 1 in 6 chance of rolling a 5. But what is the probability of it not being a 5? That, my friends, is called the opposite, or complement. And those of you who are actually thinking about that will probably recognize that that is 1 minus P of A. In the case of you not rolling a 5, it is 1 minus 1 over 6, which is 5 over 6. So the probability of not rolling a 5 is 5 over 6. This doesn't sound complicated, but the idea of 1 minus P of A being the opposite or complement is actually very important. But if you want to know the odds of the outcome being... Alright, so they continue on, and they actually get, it's a pretty good example to go into more detail about probability, but that's as much as we really need to know for our examples here as we go to the next couple slides and talk about probability in psychological testing. So, scientists in general have decided that 5% is a pretty good standard. We call it the alpha level, so we measure it in these tests. We do a p-value assessment, and we say, okay, this had an alpha of 0.05 or 5%. There's a 5% chance that this difference came from chance. There's a 5% chance that this result came from chance. That is acceptable, right? So psychology uses that standard. Like I said, I usually use the standard of 1%, just having a little bit more strict, a little bit more conservative assessment there, just a 1% chance that the result came from chance. That's what I would prefer to see. So this would be that there's about 5 chances out of 100 that the results were due to random chance or random error. So error in the measurement, mistaken problems in assessing a true score versus not assessing the true score. Basically just a 5% chance that your result came from chance. That's the standard in psychology we've accepted. Generally, that will be the standard a journal uses. I've seen some say in their requirements, like they will accept that, but they would prefer 0.01, so 1% chance. But I haven't seen myself any that require the more strict one yet. So if we think about our example of flipping heads, 10 heads in a row is this. P equals 0.00098. So I did that calculation. That's what it is. So 0.098% chance, or 0.098% chance that the results came from chance. So how many heads in a row equals 0.05? Take a guess. Or if you're really good at math, or have a calculator and are really good at math, you could calculate it out. So what do you think? So 4 heads in a row is a 0.06% chance. 5 heads in a row is a 0.03% chance. So right between 4 and 5 heads in a row is the probability of getting 4 and 5 heads in a row. So take that with the sense that that's kind of the minimum standard of chance in psychology studies, right? A 5% chance is somewhere between 4 heads and 5 heads in a row. So is that conservative enough for you? For me, not quite. Yes, 4 heads in a row is pretty impressive. 5 heads in a row is more impressive. But what do you think? Is this significant to you? Is this statistical significance enough? So obviously the penny example is actually just chance. There's a 50% chance of it landing on heads, right? So it is actually chance. But what about 0.05 in actual experimental results? When we look at 7 heads in a row, that is a 0.015, so that's a little bit less conservative than the standard I like to use, which is 0.01 without the 5 here. So that's about what I'm at. I'm at that amount of chance is acceptable for me to be potentially in the results of my studies. So and then there's 9 and 10. So I have had results that are 0.001% chance. Right? A lot of my results are, and so it's like, yep, that's pretty clearly not chance. This is probably a true difference or a true relationship between these variables. So with this, if we had this kind of result, a 3.5 for the control group and a 5.5 for the treatment group, 100 people so 50 people per group, this would be a chance of 0.03. So is that acceptable? A 3% chance that your results came from chance? Yep, for psychologists, we would say, yep, that is an acceptable p-value, the alpha of 0.03, a 3% chance that this result came from chance. We can be pretty sure that this result is a true relationship, that our treatment actually did make people more creative. So with this, as scientists, we need to be careful about using and understanding probabilities. Again, this goes back to the main point, that these are trends that we're finding, right? So here we found a trend that on average, most people who did our treatment got an increased score in creativity. Will there be people in that group who didn't have an increased score in creativity? Absolutely, right? We found it's highly likely, it's highly probable, there's a 97% probability about that the people who do the treatment will increase their creativity. So with that, it doesn't necessarily, that variable in and of itself might not let us predict any individual case, but that's why we get more variables, check out more probabilities, build the research and literature base so we can find patterns and say, okay, you have this creativity level, you have this intrinsic motivation, you have this knowledge of the field, so on and so forth, whatever variables are important, I can predict pretty well that you will absolutely increase your creativity. And if you're a person making an intervention, you want to do the best you can to know who it works for, why it works, these kinds of things. All right, so that builds really well into Chapter 11, which is a lot shorter, but continues on with statistical significance and confidence intervals. So with this, with actuarial prediction, with using these predictive models, with using probability equations, before we accept any complicated explanation of event, we do need to consider what part chance may have played. So that's what null hypothesis testing does. It hopefully makes sure that our explanation is the right one and it wasn't just chance, but sometimes things just happen by chance. So statistical prediction does show that there is a high likelihood of our actual result happening, But it also says that, yes, there are going to be errors in measurement. There's going to be errors in measuring human behavior. There still is, in that most recent example, a 3% chance that that result came from chance. That's still a possibility that it was just random, right? That it was just a random occurrence or random error or any kind of other uncertainties that led to that result. So with this, humans don't do a really great job at seeing chance and understanding how much effect it can have. So some things that happen in life are totally completely random. Like they said in the video, if we see a pattern, we can then maybe predict it better. But some variables are affected by multiple variables, and then having a better assessment of all those variables, we can make a better prediction. Some variables can be predicted with really great accuracy, and that's what we want to do as a science, is have a better understanding of all the variables that are relevant to be able to make really good predictions. So, sometimes a thing might happen that looks like it's correlated, but it might have just been chance, right? So that's something to consider. Is yes, we need to understand that we as humans, we do a really good job at finding things that seem to be connected to one another. It doesn't necessarily mean they are. That's why we need to do good testing to make sure that these variables actually are correlated and it's not just happening by chance. So humans are very, very good at making meaning out of things. So basically pulling meaning out of things that appear random. So as I was walking past a really big tree today, I hit it with a stick. Soon after that, I heard thunder. Are those two things related? We might, as humans, make meaning between them, right? We might create a mythology around some kind of behavior of this tree affecting the weather. Humans can do that. We're really good at putting things together, at seeing relationships, even if they aren't necessarily there. This is one reason we need this kind of good statistical analysis to see, is this likely chance or is this likely actual data? So personal coincidences can be very memorable. They can be really important to us. They can be really relevant. That example of the one uncle that didn't get lung cancer, that might have been our favorite uncle. So it might be very important to us, be very meaningful. So we might hang on to that a lot stronger than other things. So humans do a really good job at making meaning out of things. It's one thing our brain is really good at, and it can be very useful for building relationships with people and things like this. But with that being said, even if something is very unlikely to happen, it is possible that some things can just happen by chance. So we might call it destiny when it's actually just a coincidence, that just by random chance, that thing would happen at some time. So that's one reason that doing these kinds of statistical tests is very important. So we can't ever be 100% accurate, but we try to get as close as we possibly can. We do that with these kinds of methods we've been discussing the entire class. The better our methods leads to better statistics, then doing the proper statistical analysis can get us at the closest kind of answer that we can get. So we need to admit that we can't be 100% accurate all the time. We can be pretty sure, we can have a very good sense of probability that people will get lung cancer from smoking, but not that every single person will. Like, we're not going to be able to be 100% accurate, but we're going to try to get there. So let's take a pretty simple example. Let's say a red light flashes 70% of the time and then blue 30% of the time. So as this light is flashing, let's say it flashes every 2 seconds. So flashes, flashes, flashes. 70% of the time, it's a red light, right? So if you guess red, so if it turns off and someone says, hey, what do you guess next time? If you say red, I predict it's going to be red, you're going to be accurate about 70% of the time, right? So if you're just guessing red, but some of the times you won't be right. That's what an actuarial prediction is, using the statistics, using these probabilities, using these percentages, looking at our samples and relation to our populations to say we can be pretty sure, or for most people, or for these specific groups, that this is what we predict, this is the relationships that exist, this treatment will work. That's the kind of thing we're doing with actuarial prediction. Actuarial prediction specifically tries to make a general prediction that'll be right most of the time. So in this case, you're guessing red for this flashing light. You're going to be right most of the time. Not all of the time, and you accept that, but you'll be right most of the time. So we can make actuarial predictions based off of things like statistical records, using inferential statistics, using census data. All of these things can be used to create a good actuarial prediction, so we can get pretty close for maybe most people, or if we know multiple variables, we can probably do even better at making even better predictions, and that's the point. So Stanovich, one of the main points near the end of the book, is saying that actuarial predictions are better than clinical predictions. Basically what a clinical prediction is you have a clinician interview a client rather than doing assessments of the client. A clinician might, based on that interview and knowing something about the variables, make a diagnosis or a prediction about the person. Research shows that these actuarial predictions do a better job. So humans tend to see relationships where there might not be any there. Actuarial predictions can help us with that, to make sure that we're doing better predictions, that we're using these probabilities, using these statistics, these inferential statistics in a good way to make good predictions. So again, as scientists, be careful about using our understanding of probabilities. We know that we're not 100% accurate 100% of the time, and with only knowing a few variables, we might not be able to predict any individual case specifically. So thinking back to that airplane example. But if you know all of those variables and you know, oh, this person can fit in this scenario, then we can be a lot more likely to make a good prediction about them. But if we just use one number or look at people on average, we're not going to do as good of a job. So with that, this also goes back to looking at patterns of data. So again, that was talking about individual studies and results, but this kind of parallels with the bigger, broader sense of how do we shift from one theory to another theory. So we look for patterns of data. We look to a new theory has to explain everything the old theory did and all the new information too. So the new theory explains the new stuff and the old stuff. So this is some of the main final points of the Stanovich book, and some of the main final points to keep in mind as a scientist, that this is how we test things, this is how we understand things, and while we might have to do these kind of actuarial predictions and not have 100% certainty, the better we can do at methods, measures, and statistics, the better we're going to be doing at our predictions, and hopefully getting at a better prediction with understanding more things and more relationships. So hopefully the math from this section didn't freak you out and you understood the examples that we gave. Definitely let me know if you got 10 heads or 10 tails in a row, and I believe that is the end of this book. So I'm glad we finished that. Hopefully you saw some of the patterns repeating throughout Stanovich's work, and you learned a lot about the science of psychology through the Stanovich book.